All right, I want to talk about demand-price relationships. And for demand-price relationships, we're going to be looking mostly at just a linear relationship between the two. And that's not necessarily the way things are in real life. There could be a nonlinear relationship between the price of an object and its demand, but we're not going to look at it that way. We're just going to investigate a situation, and typically this will have a negative slope to it like this, and we might have the relationship price equals minus some slope, let's call it B, times the demand plus some constant A, which is associated obviously with this price at zero demand, or the intercept. So again, our slope here is essentially minus B. Okay, so we can use a little bit of algebra and determine that our demand then equals A minus P over B, because we're going to take our demand and we're going to use it to construct a revenue equation. Okay, our total revenue, TR, I think that's the letters that are used in the text, equals our price, P, plus our demand. Or actually, our price times our demand. I know that. I don't need to have my glasses on to see that correctly, but that's how I messed that up. And this makes sense. Say you have a demand of 4. Well, you just multiply it by the cost of each of those 4 items, and that gets you your total revenue. If 4 people want something, you multiply it by 4, the price by 4, and that's your revenue when you sell it to those 4 people. So we can represent this algorithmically with our price equation, which was this curve from above, BD plus A, that's our price, and then we multiply that by D again, which turns this into a quadratic equation. B D squared in D plus AD. And we can tell by just looking at this, because since we have a negative here, that this is going to be a concave down parabola. So it's going to look something like this. We're going to have a curve that looks something like this, and that will give us a distinct maximum. So if I plot this curve, it's going to look something like this. Just a parabola with a distinct maximum. Now, where's that maximum at? Well, the location of that is going to be at A over 2B. If you remember back to your pre-calculus probably, or calculus, that's a quick way to determine the center point of that. You can also differentiate this and find that because this is a maximum point. And maybe the easiest way to remember that is think of the quadratic formula, ax squared plus bx plus c, and the solution to that. And this is something everybody should try to memorize, actually. B plus or minus the square root of b squared minus 4ac all over 2a. So we could actually put this over 2a and this over 2a if we wanted to. Well, when you have concave up, a is going to be negative. So this is going to be a positive value, and that means this is your location, essentially, of your your center point. And then you go plus or minus a certain distance from that to figure out where these points cross the curve, because you set this equal to 0. Well, in our case, things are just mildly different. In our case, because business people want to make things just a little different so they can act like they are doing things themselves. They're gonna up here. They're gonna use the term B, which for us was, well, let's do it this way. For us, our A is little b up here, of course, and our B is little a. So that's why you get A over 2B now, as in the book. So in our case, we could take this A over 2B and stick it in for D in our total revenue equation to find out what the maximum is. And of course that's minus B. And we can do some algebra, and we end up with minus A squared over 4B as our maximum. Okay. Maximum value for revenue. So, profit. We're going to call profit, may as well spell it out so we don't confuse it with price. Profit is our revenue, spell it out again, minus our cost. So we calculated revenue up here. And so now we've got to kind of look at cost, so we can figure out what those are. Well, cost, we can say, equals whatever our fixed costs are, plus possibly some variable costs. So I'm just kind of arbitrarily putting costs in here. These aren't the only ways you might set up cost in your life. So our fixed costs are just going to be constant then, and our variable cost will be functions of D, our demand. So essentially we'll have fixed cost plus something we're going to call CV times D. So it'll be some little cost increment times each unit that we have. So if we have 5 of these things, we'll multiply them by 5. Whereas the fixed cost is always the same. Maybe that's the cost for renting the place we make the equipment. So now our revenue equals total revenue minus total cost. So we can stick in these little linear equations we set up here for our revenue. First off, we have the quadratic equation again, minus BD squared. So quadratic in D, in demand, plus AD. And since we're doing that in terms of demand, may as well just decide to do our cost. So we have our fixed costs, which are constant, plus this cost increment, variable increment for a variable cost, which is function of D. So we multiply it by D. So it's just a linear function of D. So it's a line. It's a positive line with a slope of CV, essentially. And again, this is going to produce a different parabola, which is minus B D squared plus A minus CV. We have two terms that are functions of D minus CF. And this, of course, is in the AX squared plus bx plus c, general format. So we can optimize this. This time, instead of optimizing, so optimize. This time, instead of optimizing with what we know, how parabolas behave, let's just do it the algorithmic way and take the derivative of profit with respect to demand. And so this is going to be minus 2 B D star plus A minus CR. And here D star represents actually a term A minus CR over 2B. Okay, so let's do a little bit of graphical analysis here. So we have a revenue curve that we calculated up there. But now when we incorporate profits into our relationship, we have a different parabola, which is a profit, our profit curve. Again, this is function of demand. That's how we set it up. And this too has a max. And we found that a max was at this value we called D star. Now, when we come back and look at our price curve, the D star value is over here now. So, and that's because our cost curve comes into play in the next. And our cost curve, remember, this intercept point is CF because the cost curve is just this linear equation. This has a slope of CV, and yeah, that's our cost curve. So we have a max profit point over here, and notice that max profit point is not at the same level as our max revenue point, and that's due to cost. So let's talk about our break-even points. Now these occur, if you think about it, where our costs encounter our revenue curve. So if we set our total revenue equal to our total cost, we should be able to calculate those points. So here we go. A times D minus BD squared, demand squared, equals our fixed cost plus our variable increment times our demand again. And we can solve this. This gives us another quadratic equation, and it gives us the intersection points here. And we can use the quad formula, and you could solve that relationship if you had the parameters. So one other way to look at this is you can look at this yellow line, this yellow cost line, as the cutoff line for any demand, whatever it may be. Then you can see that if we go above the yellow line, we're going to have net profit because we're going to have more revenue than cost. However, if we're below the yellow line, we have a net loss. So you could potentially shade in the area above this line under the profit curve or the revenue curve. And that is our net profit, and net loss is the area below here. And that's where I'm going to stop.